Okay, let's take a look at entire radicals and mixed radicals, part two. So we're again converting between mixed radicals and entire radicals, and now it's just upping the level of difficulty a little because we're not dealing with just square roots, we have an index. So remember, the index is that little number outside that radical symbol, and so that index we're looking at greater than 3 or 3 or more. So again, if we know that we've got an index of 3, we're talking about cube roots, it's handy to have a list of perfect cubes to look at so that they're just easy to access for you to recognize what the perfect cube factors are for your radicand. So if we take a look at that first example, to convert the cube root of 54 to a mixed radical, so the entire radical being the cube root of 54, so the mixed radical, so what perfect cube is a factor of 54? So obviously we're looking at either 27 or 8. One doesn't matter because that's not going to change anything. So it's obviously going to be 27. So the cube root of 54 can be rewritten as a cube root of 27 times 2. Or we can split them up as a cube root of 27 times a cube root of 2. But of course, a cube root of 27 is actually 3. So because 3 cubed is 27, so we can rewrite this as 3 cube root 2. And so you just want to make sure that you're careful with that little index, that it doesn't become too big, that it doesn't move over and look like it's an exponent of your coefficient either. Okay, so let's take a look at the cube root of 6,000 if we want to convert that into a mixed radical. So going through our list of our perfect cubes, we can see that 1,000 is a perfect cube, so we can split that up as a cube root of 1,000 times the cube root of 6, and the cube root of 1,000 is 10, so we're simply talking about 10 cube root 6. And again, these are all things that we can verify on our calculator using decimal approximations as well, since they're all irrational values. So if we're looking at an index that is not 3 or not 2, then we're accessing, our knowledge of our perfect fifths. And so if it helps you, then write some of them down. I'll tell you even the extent of what I know about those values doesn't go up very high either. So 1 to the 5th is obviously 1, but that's not relevant. 2 to the 5th is 32. Oh, thank goodness. We don't have to go much further than that, and so we can see then that the 5th root of 320 can be broken down to the 5th root of 32 times the 5th root of 10, and the 5th root of 32 is 2, so it is 2 times the 5th root of 10, and that is our mixed radical in simplest form. The cube root of negative 16. So of course, because we have an odd index, it is totally fine to have a negative in your radicand. However, that is important to note though, because if we are simplifying, we would like the negative to come out. So if we then are looking to simplify the cube root of negative 16, my perfect cubes, if 8 is a perfect cube, well, so too then is negative 8. So then we've got the cube root of negative 8 times the cube root of 2, and the cube root of negative 8 is negative 2. So we're looking at the negative 2 times the cube root of 2. And that is what's simplified. So that would be preferred than saying the cube root of 8 times the cube root of negative 2 and leaving the negative 2 inside. Ideally, always bring that negative outside. Okay, so if we're converting a mixed back into an entire, it's the same thing. You want to take whatever that coefficient, whatever that number is outside, and apply the index as your exponent. So if I've got 1/2 times the cube root of 80, then what I want to do, and I can put that over to the side, is I can say 1/2 cubed is the same as 1/2 times 1/2 times 1/2, or 1/8. So 1/2 is the same as the cube root of 1/8. And so then cube root of 1/8 times the cube root of 80, we can combine them as a single radicand, and 1/8 times 80 is of course 10, so then we are talking about the cube root of 10 as our entire radical. Okay, so let's take a look at class example number 2 then. So it's just more practice of that same thing. So 2 times the 4th root of 3. So since our index is 4, I want to think to myself, what is 2 to the 4th? And that is 16. So we're looking at then the 4th root of 16 times the 4th root of 3, and that is also known as the 4th root of 16 times 3, or 48. In this particular case, with that negative is not going to get lost, because when I cube it, it's still going to be negative. So there's no issues there, as opposed to if we look ahead to example D, that negative will get lost once we raise -3 to the 4th. So we'll want to leave that negative out front. So if I cube -4, it's the same as -64. So I've got the cube root of -64 times the cube root of 7, and multiplying that all out, then we've got the cube root of 420, and 28 is going to be -448. And so if we take a look at the next one, then 2/5 times the cube root of 100. So I want to then cube 2/5. And so if it helps just to write stuff down so you can see it, and so you're not forgetting what you're doing, whoops, and that is cubed, not squared. So then 2 cubed is 8. 5 cubed is 125. So then I know I'm looking at the cube root of 8 over 125 times, and I'm going to do this all together because I know I'm going to be able to simplify, 100 over 1. And then we know that 100 over 125 reduces by 25, so that will go in 4 times, and that will go in 5 times. So then we are actually looking at the cube root of 8 times 4, which is 32 over 5. Then for D, we mentioned that that negative, if I raise -3 to the 4th, it's going to be +81, which means that that negative gets lost. So that negative is just going to hang out outside, and then we've got the 4th root of 81 times the 4th root of 2, so that is negative of the 4th root of 162. Okay, so it's some tricky stuff, but take your time with it, and let me know along the way if you've got questions as well. So using variables as well, the same thing that works with numbers works with variables. Where people get tricked, so to speak, though, is that people say, hey, well, x to the 9th, and they look at that number 9 and they think of that as being, well, since 9 is a perfect square, then x to the 9th is a perfect square. That's actually false, because if you think about it, if I was to write out 9 x's, how many do I have here? 6, 7, 8, 9. Could I split that evenly into two groups? I can't. Closest I could get would be x to the 4th times x to the 5th. And so x to the 9th is not a perfect square. Whereas if I take something like x to the 6, if I write that out, we've got x times x times x times x, times x times x. In this particular case, I can split that into two equal groups. So then we've got x cubed times x cubed. So x to the 6 is then a perfect square. Okay, so you can see right here they've got x cubed times x cubed is x to the 6, so the square root of x to the 6 then is x cubed, because you're asking what times itself equals x to the 6, and it is x cubed. So similarly, x to the 5th times x to the 5th times x to the 5th is x to the 15th. Then the cube root of x to the 15th is x to the 5th. Okay, so at the end of the day, what are we looking for? We are looking for multiples of the index. Okay, so since here we've got an index of 2, so since x to the 4th, 4 is a multiple of 2, then that will be easily simplified. So the square root of x to the 4th is x squared, because x squared times x squared is x to the 4th. Square root of y to the 10th, again, index of 2, 2 goes into 10, or 10 is a multiple of 2, divide that by 2, so that is y to the 5th. So y to the 5th times y to the 5th is y to the 10th. Square root of a to the 8th times b to the 6th, and remember we can split those up, so the square root of a to the 8th is a to the 4th, square root of b to the 6th is b cubed, so our answer is a to the 4th b cubed. Cube root of x to the 24th, we can split up all of those 24 x's into 3 equal groups, each of them having x to the 8th. Okay, cube root of y to the 6, again, 6 is a multiple of 3, and so we can split up those 6 y's into 3 groups, and each one is y squared. So y squared times y squared times y squared is y to the 6. So if we want to rewrite as a mixed radical, again, we're looking for the largest perfect square factor, or whatever that index is. So if we have x to the 5th, the square root of that, the largest perfect square factor is x to the 4th, so then we can split that up as the square root of x to the 4th times the square root of x. Square root of x to the 4th is simply x squared times root x, so the root of x to the 5th is x squared root x. Okay, looking at class example number 3, the square root of a to the 7th. The largest perfect square factor is a to the 6, so we've got root a to the 6 times root a, or a cubed root a. Square root of t to the 9th, again, largest perfect square factor is that largest multiple of 2, since our index is 2, so square root of t to the 8th times the square root of t, or t to the 4th root t. Now we're talking about cube roots, so the largest multiple of 3 that I can, closest to 5 that I can get, is going to be the cube root of x cubed times, and cube root of x squared, so the cube root of x cubed is obviously just x, so x times the cube root of x squared. So similar, again, cube root of x to the 7th, the largest multiple of 3 that I can get to close to x to the 7th is going to be x to the 6th, so the cube root of x to the 6th times the cube root of x, and so then we're looking at x squared times the cube root of x. Okay, class example number 4, same thing, it's just one piece at a time. Okay, so we'll just try these ones. Okay, so when I look at these particular questions, and there's multiple factors within our radicand, I often find it easier to just split them up and to say, hey, this is the perfect square portion, and this is going to be all of the leftover stuff. So x to the 6th is a perfect square. So I'm going to put that in the first radicand, and then y to the 4th is also a perfect square, and then that leaves me simply with y. And so x, the square root of x to the 6th, y to the 4th, times the square root of y is equal to the square root of x to the 6th times y to the 5th. And then since this is a perfect square, then the square root of x to the 6th, y to the 4th is x cubed y squared, and then times the square root of y. Okay, so similarly, then when you bring in a coefficient that is not equal to 1, so again, we're going to split up my perfect square portion and whatever is left. So the 18 is going to be root 9 times root 2. X cubed will be x squared times x. So the square root of 9x squared will be 3x, and that is multiplied by the square root of 2x. And so if you'd like, you can hit pause and try C and D on your own, and then fast forward through and check your answers, or you can work along with me. So if we split them up, then again, the perfect square portion of root 32 is root 16, and remaining is root 2. Y to the 7th, we can take out a y to the 6th, and we're left with y to the 1, and z to the 8th is a perfect square, so that's going to go totally under the first radical. So the square root of 16 y to the 6th, z to the 8th, that is a perfect square, so that is 4y cubed z to the 4th, and that is being multiplied by 2y. For part D, so it gets a little bit trickier now that we have an index that isn't 2, but again, remember, for our, for our numerical coefficient, we are looking at the factors of root 40, and so the perfect cube is 8, leftover is just 5, and then when we're looking at our variables, we're looking for multiples of 3 or multiples of our index. So x cubed, leaving me with just x, and then y to the 9th is a perfect cube because 9 is a multiple of 3. So cube root of 8x cubed y to the 9th is 2xy cubed, and I'm left with the cube root of 5x. Okay, last one, so very similar, class example number 4 to class example number 4 is this one, except there is already, oh, so sorry, I should have read the question. It says to convert the following mixed radicals into entire radicals. So looking at that index for A is 2, so 2, if 2 was under the radical, that would be the same as the square root of 4, and that is going to be multiplied by square root of x cubed, so that is then the root of 4x cubed. A squared is the same as the square root of what? So if I square it, then that is a to the 4th times, so root of a to the 4th, sorry, times root a is equal to root of a to the 5th. Again, if we square x to the 5th, so if you think about it, you could say x to the 5th, and I'm going to square that. That's the same as x to the 5th times x to the 5th, or x to the 10th. So at the end of the day, then we're saying x to the 5th is the same value as the square root of x to the 10th. Multiply that by the root of xy, and we will have the square root of x to the 11th times y. For D, then we want to, so we're looking at the cube root, so I need to take this whole thing and I need to consider, and here's another way that we could do it, is we can say, oh, I want the cube root of whatever 3xy cubed is all cubed, if that makes sense, times the cube root of 2z to the fourth. The only catch with this is you have to actually evaluate that exponent outside, so that's going to apply to each of these. So then we're talking about the cube root of 3 cubed is 27, and then x to the 1 cubed is x cubed, y cubed, and then that's cubed, it's y to the ninth, and that's being multiplied by cube root of 2z to the fourth, and we'll put everything together. So we've got then the cube root of 2 times 27, or cube root of 54 times x cubed y to the ninth z to the fourth. And that is our solution. Ideally, you're going to keep your variables in alphabetical order. Okay, and that will work for all of them. I would accept all of these answers. If you wanted to get a little bit fancier, things that you can concern yourself with, and they should always be in the back of your head, except I'm just not going to be too picky about it this year, is if we're talking about the square root, remember, what do we want to make sure that we have is that we have our radicand has to be a positive value. So that means that the answer is this only if and only if x is greater than or equal to 0 then. Or in this case, a must be greater than or equal to 0, because if a was negative or x was negative, and we cube it or we raise it to the fifth power, then it's going to leave us with a negative radicand, which we can't have. Okay, so please try the assigned questions and let me know if you have anything that's giving you some problems. Okay, thank you.